IEEE 802.11 is a crucial part of the IEEE 802 LAN technical standards, detailing the Medium Access Control, MAC, and Physical Layer, PHY, protocols for wireless LAN computer communication. This set of standards serves as the foundation for Wi-Fi products and stands as the most commonly utilized wireless computer networking standards globally. Typically found in both home and office networks, IEEE 802.11 facilitates communication between laptops, printers, smartphones, and various devices, enabling them to connect wirelessly and access the Internet. Vehicle-based communication networks, such as IEEE 802.11p, also rely on this standard. These standards are overseen by the Institute of Electrical and Electronics Engineers, IEEE, LAN/MAN Standards Committee, IEEE 802, and have seen multiple amendments since the base version release in 1997. The IEEE 802.11 family encompasses various frequencies, with examples including 2.4 GHz, 5 GHz, 6 GHz, and 60 GHz frequency bands. While the specifications outline potential channels for use, the actual availability of the radio frequency spectrum varies depending on the regulatory domain. IEEE 802.11 protocols are commonly used alongside IEEE 802.2 and are designed to seamlessly integrate with Ethernet, often carrying Internet protocol traffic. The protocol family employs carrier-sense multiple access with collision avoidance, CSMA/SATSA, where devices listen to a channel before transmitting to avoid collisions. Over time, amendments like 802.11b, 802.11a, 802.11g, 802.11n, 802.11x, and 802.11x have been introduced, each representing advancements in wireless technology with increased capabilities and efficiencies. Specifically, 802.11b and 802.11g utilize the 2.4 GHz ISM band, subject to interference from devices like microwave ovens and Bluetooth gadgets. In contrast, 802.11a operates in the less congested 5 GHz UNI band, offering more channels for data transmission. Other standards like 802.11n, 802.11a, and 802.11ax can operate in both the 2.4 GHz and 5 GHz bands, each with unique features and performance benefits. The continuous evolution of these standards caters to the growing demands of wireless connectivity, ensuring efficient and reliable communication across various applications and environments. Maximum achievable throughputs for all variations of 802.11 are typically based on measurements under ideal conditions or in the Layer 2 data rates, but this does not represent real-world scenarios. In practical deployments, data transfer occurs between endpoints, with at least one connected to a wired infrastructure and the other via a wireless link. The conversion between 802.11 WLAN and 802.3 Ethernet occurs as data frames pass through the medium, with the speed of data transfer influenced by the application's packet size. Applications using small packets like VoIP can result in high overhead traffic and low goodput. Additional factors affecting application data rate include the data rate at which the application transmits packets and the energy received by the wireless signal based on distance and the configured output power of the devices. 802.11 standards utilize different frequency bands, with 802.11b, 802.11g, and 802.11n 2.4 operating in the 2.400 to 500 GHz spectrum, while 802.11a, 802.11n, and 802.11 use the more regulated 4.915.5 GHz band, known as the 2.4 GHz and 5 GHz bands. These bands are further divided into channels with specific frequencies and bandwidths, akin to radio and TV broadcast bands. The 2.4 GHz band contains 14 channels spaced 5 MHz apart, starting with channel 1 centered on 2.412 GHz. Channel availability varies by regulatory domain, with differences in channel spacing and restrictions across countries. 802.11 defines a spectral mask specifying power distribution across each channel, requiring a minimum attenuation level from its peak amplitude at plus 11 MHz from the center frequency to prevent overlap. Channel availability is country-dependent, with rules on channel usage and power levels varying globally. The non-overlapping channels in the 2.4 GHz band under 802.11 standards differ based on modulation methods, with specific channel separations recommended to minimize interchannel interference and ensure efficient transmission. Regulatory compliance in different regions is crucial for Wi-Fi operation, with IEEE employing reg domains to denote legal regulatory areas, defining transmitter power levels, channel occupancy times, and permissible channels. Default settings on Wi-Fi devices typically adhere to the lowest common denominator for global compatibility, with restrictions on changing reg domains to prevent conflicts with local regulations. 802.11 frames consist of MAC headers, payloads, and frame check sequences, with specific address fields carrying MAC addresses for transmitter, receiver, and filtering purposes. Management frames handle communication maintenance, with subtypes like authentication, association, beacon, and deauthentication frames facilitating network connectivity and control. Control frames like ACK, RTS, and CTS serve in data transmission management, while data frames transport packets within the body, incorporating error recovery mechanisms to ensure data integrity amidst transmission challenges.